So I'm gonna record this screen about lab 5, okay? So lab 5 is about frictional forces and acceleration when the acceleration of an object when sliding uphill and downhill when the friction exists. So students are going to explore about what happens to the acceleration of an object when it slides down along an incline when there is a friction and if they change the angle of inclination. Okay. Another thing students are going to look at, explore about is what happens, how the acceleration changes if the object is sliding downward in comparison to the acceleration of the object that is moving upward along the inclined plane. Um, Another thing students are going to look at is how the kinetic friction is different from static friction. Students are also going to calculate the coefficient of static friction between the surfaces in contact after building their own experimental setup. In terms of resources and equipment, so here are the resources and equipment. So simulation from O physics. Student will need a ruler to make a measurement of the sides of the triangle, right angle triangle, and 3 different objects of their own choice. It could be calculator, phone, ball, etc., whatever they have at home that's safe to slide. And let's see, simulation can be found here. So we'll come back to that. So useful equations in part 1 here is this. This is what the maximum value of static frictional force is equal to coefficient of static friction times n, which is where mu s is coefficient of static friction, n is the normal force. Mu s is also equal to tan theta max, where theta max is the angle at which the object starts to slide along an inclined plane. If k equal to mu kn, this is the equation for kinetic frictional force. In both of these cases, this first equation and this equation, n is cos theta component of weight, which is mg cos theta. Other useful equations are these two here. For uphill motion, total sum of the force is equal to kinetic frictional force plus x component of weight force. For downhill, same equation except it's negative sign here, which means this total value of force here should be smaller than the value of force we find here in uphill motion. That also means the object that's accelerating the object that's sliding downhill will have less acceleration than the same object if it was sliding uphill. Now, students will need help with this part, I think. Draw a free body diagram of an object of a mass m moving downhill along a plane inclined at an angle theta. Assume friction exists between the mass and the incline. So it may be helpful to kind of, maybe even like make a screenshot of something like, like this here, maybe like a tiny screenshot of like downhill motion or something like this. Posting this on the team may be helpful. So number 3 here is this number 3 makes use of the simulation for this part. So what the students need to do is this. So let's go to the simulation here. In this simulation, the only thing that needs to be changed here for this simulation in number 3 is this. The v naught, initial velocity of an object. So that can be, you can slide. So to make it more precise, you can use the arrow key on your computer, so it's much okay now. And make sure student keep it at 0 meter per second, okay, the initial velocity. Then nothing else need to be changed. So for the first part, really this. So we can just start at angle theta. If we run it, it's gonna look something like this. Oops. So make sure the student kind of stop. I guess we don't have to make sure it really like, but it may be helpful to just pause this simulation before this object kind of keep going. It keeps going like, I don't know, up to I guess infinity. So we don't need that part anyway. Here, so that is the acceleration here, 2.35 meter per second is square. That was simulated value. So for number 3, what students are going to change is this angle theta. So if you keep changing theta and look at the value of acceleration here, okay, so that's it. But before they get here, so this is the simulated value, but students also need to do the theoretical calculation for each angle, right? So to do the theoretical calculation, they can use this angle, right? Sorry, this equation here, downhill equation. Student actually may even need help more than that. Just we may have to, maybe it may be helpful to just take a screenshot of this part here and then just give it to them or something like that, okay? So which is what mg sine theta minus mu k times n equal to m times acceleration in x direction. And from that they should be able to just get a, because they should have mg sine theta. This n also has what, mg cos theta, so m and m gets cancelled from everywhere. So all they really need is what is g and then theta and then mu k, which should be, they can use this from simulation part, and then again the value of cos theta there. So and then after that, organize data. Students can organize data in a table like this here, and then they can try for two more angles here and here, and then just see if the values agrees or not. They should agree, just like what it's shown here in this student's answer sheet. They should kind of agree pretty close. This value and this values, yes. Next one is here, number 4. So is the acceleration of the block sliding uphill equal to acceleration when the block is sliding downhill? Draw two separate free body diagram for uphill and downhill motion along a plane inclined at an angle theta for an object of a mass m moving along the plane. So again, the students may need help here. They may need to be told why, like in one case the frictional force and the weight component, or kinetic friction and the weight component add here, and then in this case the weight component along this line and the frictional force, they kind of subtract to each other. So really again simplifying this equation, right, like equation given here. So this part is they may need help there. Now for the simulation, here is a hint given, so I think student will also know how to do this since they are told here. So change the initial velocity to the maximum value for both uphill and downhill motion. You can use slider. So really, instead of keeping at 0, this could be just kept, maybe let's do the positive. It's going towards downward here. That's the positive side, and then let's say if we run it, right, and pause it. Okay, so that's with the initial velocity, and then if we do the other way, and then I think it can be again run and then pause this. Okay, so you see the value of the acceleration changes there. And from the experiment, they should find that the acceleration uphill is much greater than this acceleration downhill here, which is this. Okay. Number 5 here, predict whether the static frictional force is greater than the kinetic frictional force. Choose one angle and based on the data given in simulation, verify your prediction. For number 5, they don't need to do any experiment or simulation. All they have to do is really use this equation, right? Like equation given for static frictional force and then kinetic frictional force, and then basically solve. So it's kind of like this here, right? Fk is mu kn, and then fs is mu s n. So just really mu s, and the n is what? Mg cos theta, value of mg, mu s, and theta is, if they choose one angle, they should have all of those information. And value of mu s and mu k will also come from here, from the simulation. Okay, so mu k, mu s, m, right, z, and then theta. So that should help them figure out the answer for that. So this part is only calculation. Okay, number 5, no simulation or experiment. Number 7, so this is where students need to choose the, they need to build a ramp using, maybe they may have a chopping board at home or part of cardboard box or thin book, etc. That could be used to make a ramp, and after they make a ramp, they can use a calculator or cell phone to, to slide on the ramp. Okay, important part here is this. So this part is like, do you see the right angle triangle formed by a ramp in this arrangement? Calculate the angle of inclination of theta using trigonometry. So right, tan theta, basically we need here tan theta. So anyway, they should be able to calculate the theta when they have a ramp that forms a right angle triangle after measuring the dimension of the triangle. Now then find tan theta, find another small object, example this, and place it on the ramp. Then experimentally determine at what value of theta the object on the ramp begins to slide. The tangent of the maximum value of theta at which the object starts sliding corresponds to coefficient of static friction between the surfaces in contact. Okay, so this part is where student may need help. So they should kind of start from a small angle. Let's say I have a calculator on the ramp, and then it can actually, so I can start somewhere maybe like from 5-degree angle, and then let's say it doesn't, slide, calculator doesn't slide at 5-degree, then I can increase the angle, maybe make it 7 or 10 or 12 or something, and then find the angle at which the object starts to slide. So that value of theta, the tangent of that value at which the object starts sliding, that will give us the value of mu s. So tan theta of the theta max here, right? The theta max is the angle at which the object starts sliding. So that will give us mu s, and that's how students can find the coefficient of static friction. And then number B says just repeat the process for 2 more objects, so some other objects could be used. That's about it for research question here, part 2. It has the same structure like the past research questions. Students can either use simulation, or maybe they could just use their experimental setup, maybe try different, right, adding more mass or changing surfaces in contact or something like that. Should be, yeah. So that's about it for lab 5. Okay, so I have already posted this students copy and then lab 5 handouts on MS Team, so you should be able to find that. Okay, all right, that's about lab 5.